Every year, chronic diseases such as colon cancer and kidney disease affect millions of people globally. Yet, the treatment options available still fall short in terms of safety, affordability, and long-term effectiveness. At the same time, there's a growing interest in naturally derived, plant-based pharmaceuticals, especially those that can be produced sustainably and with minimal environmental impact.
That's where our project comes in. We're focused on producing a pharmaceutical-grade inulin, which is a plant-based polysaccharide from Jerusalem artichokes. Inulin isn't just a dietary fiber. It can be used as a carrier or a stabilizer in drugs targeted at the kidney or colon. But producing ultra-pure inulin suitable for injection isn't just a simple process. The problem, most current inulin processing methods are optimized for food-grade applications. Our challenge was designing a process that met pharmaceutical purity standards while maintaining economic viability and being scalable.
Major criteria and constraints in our design include achieving over 90% purity while keeping product costs within limits suitable for pharmaceutical applications. Environmental constraints such as water usage, waste generation, and energy consumption are also factored in to ensure sustainability. Other potential solutions considered included processing inulin from chicory or dandelion roots, but Jerusalem artichokes were selected due to their higher inulin content and hearty growing season.
This project aims to optimize the extraction and purification parameters of a water-based process, which utilizes a number of energy-intensive unit ops, such as chromatographic separation, filtration, and evaporation methods. Experimental results from literature guided our equipment sizing, purity goals, and thermodynamic assumptions as we worked to optimize this process to balance both pharmaceutical industry requirements and general engineering principles. Our process consists of three major stages, with it starting off in the extraction process, continuing through purification, and ending with water removal. Jerusalem artichokes enter into the extraction phase, first being washed and shredded before placed into a hot water bath for liquid-liquid extraction. This separates the solids from a crude inulin mixture, which includes impurities such as fiber, ash, carbohydrates, and protein. When modeling extraction, we realized that aspen would not be able to be used due to the fact that inulin and other impurities are not a recognized material in the program. Therefore, we switched to modeling the entire process using a combination of hand calculations in Excel and MATLAB codes for our more complicated unit ops.
The inulin mixture then undergoes an extensive purification process, beginning with the calcium carbonate and carbon dioxide mixture. This stage mainly focuses on monitoring and adjusting the pH for the further steps of the purification reactors. This step also includes removing the unwanted acidic impurities. To better understand and optimize this reaction, we modeled it in MATLAB to see how adding the additional calcium carbonate and CO2 would change the pH of the inulin water mixture. The purified inulin mixture then passes through the activated carbon. This decolorizes the system and gives it a pure white color without impacting mass flow. The next step of the purification process is the nanofilter. This uses a membrane to separate the water from the large molecules. This mainly removes the water and rejects the inulin compounds and also removes a little bit of ash. The large inulin compounds are mainly rejected from the filter, with some smaller minerals sneaking through to the next steps of the process.
We had initially intended to use a desalinization unit in place of our nanofilter. We opted to use a nanofilter instead due to economic and environmental reasons. Using a nanofilter reduced our overall toxic resin usage. This helped create a more environmentally friendly process. The final stage in the purification process is the chromatography column. Chromatography, specifically moving bed chromatography, is used in pharmaceutical industries to purify substances at a large scale. Moving bed chromatography uses a series of valve switching and flow of a desorbent, which in our case is deionized water, to help aid in a more efficient separation process. In our process, chromatography uses a potassium-based resin to remove carbohydrates such as fructose, glucose, and sucrose from the inulin. The carbohydrates leave the process in the extract stream, while the inulin leaves the process in the raffinate stream.
After purification, the inulin mixture travels through an evaporator and spray dryer to remove excess moisture and aid crystallization. The evaporator is a falling film process that concentrates the product from 15 bricks to the final bricks of 35. The spray dryer uses an atomization spray nozzle to turn the inulin into fine particles, while hot air causes remaining water to evaporate, leaving the inulin in its final crystallized form. Although high users of energy, this drying schematic is essential to produce final inulin powder.
The inulin extraction process starts with sustainable, all-natural ingredients. At the heart of it all, 400 kilograms per hour of Jerusalem artichokes, packed with 69% inulin by weight.
Over 7,500 kilograms of water per hour was used to extract and purify inulin, moving through a series of clean, environmentally friendly steps, resulting in 260 kilograms per hour of 94% pure inulin ready for advanced medical application.
The byproducts generated in this process are minimal and mainly consist of water and solid plant material. Since no harmful chemicals are used in this process, these byproducts can be safely disposed of simply by dumping them down the drain.
Over the course of a year, our process consumes 5.5 million gallons of processed water, 12 million kilowatt hours of energy, 4.2 million pounds of steam, 12.3 million gallons of cooling water, and nearly 37 million liters of high-purity deionized water. That deionized water alone costs over $52.9 million a year. Add in the cost of electricity, steam, process, and cooling water, and our annual utility cost is $53 million a year.
The total capital investment is $1.08 billion. Over the projected period, the revenue is $312 million.
From an economic standpoint, our analysis indicates that the proposed project is profitable. The total capital investment is approximately $1.08 billion, while the net earnings are estimated at $312 million, resulting in a return on investment, or ROI, of 28.81%. This ROI suggests that the project returns nearly 29 cents for every dollar invested. Despite these encouraging financial metrics, there are a few key economic hazards that we do want to keep in mind. These include fluctuations in our raw material costs depending on the season, as well as costs of utilities and risks of equipment downtime in our batch processes. We also want to keep in mind any volatility in the market for our product.
Jerusalem artichoke were the best source of inulin due to high yield, safety, and low cost. We also determined the process works.
So what's next? Our next suggestion includes running a pilot test to make sure everything runs smoothly in a continuous operation. A deeper look into our waste streams to see how we can reuse our byproducts, and a more in-depth cost breakdown looking at energy usage and drying efficiency. Thank you for listening!